We will continue. Okay, I think recording has started. Good afternoon, everyone. So welcome to the my third session, and today's I think final session for you, fourth session for you. Overall, my third session. So we were talking about depth first search, and then we talked about depth first search for directed graphs. We talked about pre numbers and the post numbers. So this is the sequence under which a vertex is first, the exploration first start at a vertex, and the post number is the time when you complete the exploration at a certain vertex, right? So in the screen, you can see these numbers. Like 1 and 24 is the timestamps in which exploration started at A and completed at A. So for instance, if you look at H, the exploration started at timestamp 5 and exploration completed at timestamp 16, right, for H. Okay, so that's just 1 second. Yeah. And then we saw how to use these timestamps, these post numbers, to determine if the graph, if a directed graph has a cycle, right? Then we saw how to do the topological sort. Basically, you order the vertices in the reverse order, descending order of the post numbers. That gives you this topological sort, provided the graph is acyclic. And then we started discussing about strongly connected components. So strongly connected components of a directed graph are those subsets of vertices where if you pick any two vertices, so the one circled here are strongly connected components. So if you pick, say, J and K, for instance, there is a path from K to J, and there is also a path from J to K. So in a strongly connected component, for any pair of vertices U and V, there is a path from U to V as well as a path from V to U. Right? So the what I've circled here are the maximal strongly connected components, right? And these two are singletons. So now the question is, how can we find the strongly connected components of a graph? And then we also notice this thing that if you look at the graph with the strongly connected components, or the graph of the strongly connected components, the meta graph as I called it, then you get a DAG. Basically, you cannot have cycles here, because if you have a cycle, then all the vertices in the cycle would form a strongly connected component. So we will not have cycles in this graph. Okay, so now the question is, given a directed graph, we want to identify the strongly connected components. How can we do this? And then we noticed that if we start exploration at a sink strongly connected component, meaning sink, so in this DAG, you start from a sink, okay? So for instance, there are two sinks in this DAG, which one is D and one is this one, GHIJKL. If you picked any vertex in one of these sinks, then what you will end up exploring is all the vertices in that strongly connected component. So if you started exploring at D, then basically you will stop exploring at D. But if you started exploring at H, for instance, then you will explore all these vertices before completing. Okay? So that is how you will recover one strongly connected component. So the question is now, how do you figure out a vertex in a sink strongly connected component, right? Right. So if we started exploration from a vertex in a sink strongly connected component, then we'll terminate once we explore the entire strongly connected components, which contains that vertex. But next question is, now how do you even get such a vertex, right? How do you even get such a vertex? So again, since everything is so far is based on a depth first search, we can use depth first search itself to get such a vertex, right? Right. So the thing is, it is not that convenient to find out a vertex in a sink strongly connected component, but you can do something else. You can find out vertex in a source strongly connected component. So the claim is the following. right? The claim is that if you do the depth first search in any order, right? So if you, meaning you do the depth first search in a directed graph G, the vertex that receives the highest post number must be in a source strongly connected component. So, okay, so let's just check this claim. In this graph, there's only one source connect, SEC, which is A, and this receives the highest post number. It is not because we chose A as a starting vertex. If we chose A as a starting vertex and we got this, but let's say even if we had chosen B as a starting vertex, then we would have explored all of this. Then we would have started a new exploration from A, and then again A would have been the last number to be accepted. If you used, let's say, if you started from C, then you would have recovered all of this first. Then if you start from A, then you would, again, A will have the last post number. So this is one example that we can illustrate. Let's say here, there's a DAG without cycle. So here also, if you see, A received the highest post number, and that happens to be a source, right? So there is no here each vertex is a singleton strongly connected component because there are no cycles, right? Maybe we'll just see one more example that we already worked out. Here, what are the strongly connected components in this graph? Anybody? So AB, ACD seems to be 1.
ABEF.
ABEF, is it? No, you cannot go back to A. So BEF is 1, I think.
No. Yeah.
BEF, this seems to be 1. ACD seems to be another 1. I think that's it, right? G and H are individual. I don't think there is. Yeah, I don't think there is anything else. So, and here, what is the source? So maybe I'll just like draw the meta graph somewhere here. So ACD, BEF, uh, G. So maybe I'll do H first and G. So A has outgoing edges to B and F. D has outgoing edges to H, so this will be the one. Then BEF has outgoing edges to G and also H, and H has outgoing edge to G. So I think that's about it. So there is only one source strongly connected component, that is ACD, and indeed A receives the highest post number. Right? So that's another. There's only one source and one sink over here. Okay, so that's another illustration. Anyway, this is just to verify that this proposition is indeed correct. Now the question is, how do we show this, or rather, okay, we'll see how to show this, but okay, maybe we'll first show this, right? So it follows from the following. It follows from the following fact that if C and C prime are two strongly connected components, and if there is an edge from C to C prime, then the highest post number of C is greater than the highest post number of C prime. So what I'm saying is, if this is a strongly connected component and this is a strongly connected component, these are two SCCs, and there is some edge, there is at least one edge, maybe there could be more, then the highest post number in C is greater than the highest post number in C prime. It's not that difficult to see why this is the case, right? Suppose you start the exploration. Okay, so you start the exploration from somewhere. At some point, you will discover one of these two, strongly connected components, right? C or C prime. Suppose you discover C before C prime, right? Then you will you will you will you will you will at some point you will discover the vertices of C prime during that exploration itself, because there is an outgoing edge, at least one outgoing edge. Can there be an edge like this? Can there be an edge from C prime to C? Let me see who's paying attention.
No, no. If there is, if both are SEC and strongly connected components,
We cannot
there
have
won't
such
be
an
any.
edge, because these are both strongly connected components. And if you have an edge like this, then they would both be part of the same strongly connected component. Or in other words, it's kind of violating the what we said earlier, that the metagraph is a DAG, right? So this edge would form a cycle. Anyway, so if you first discover C, at some point you discover C prime, and then once you enter C prime, you will exhaust all the vertices in C prime, and then come back to C before exiting from C. So the highest post number will be from C, right? The whichever number from whichever vertex from which we exit from C will have a higher post number than all the vertices in C prime. Okay. That is case one. And case two is you visit C prime first before C. That also can happen. But if you visit C prime before C, you will completely visit all the vertices in C prime. So, and it will have certain, let's say there is a vertex X that has highest post number. The entire would not have been discovered at this point, because there is no edge like this. No vertex in C would have been discovered as a result of the exploration in C prime. Right? There is there won't be any edge like this, and there won't be any edge like this, like which leads to another component, and then that leading to this, because that also creates the same issue. So you would complete the exploration in C prime before you start the exploration in C at some point. So which means all the pre-post numbers of C prime would be disjoint from all the pre-post numbers in C, which means all the post numbers of C will be higher than all the post numbers of C prime. In fact, all the pre-numbers of C itself will be higher, right? So that is the reason why if you have two strongly connected components, then and an edge from C to C prime, the highest post number in C will be higher than the highest post number in C prime. Okay. Now this means that if you have a source strongly connected component, the source uh, will have the highest post number, because if it's a source, it only has outgoing edges. So you can order the DAG in some way, and there will be at least one source. A DAG can have multiple sources, but there will be at least one source, and that source will have higher post numbers than any other vertex, any other strongly connected component, or any yeah, or maybe I should say that the highest post number in that source will be higher than any other strongly connected component that you can reach to. The highest post number in any other strongly connected component that you can reach to. So this would imply that what we said earlier, that the source strongly connected component, or at least one source strongly connected component, will receive the highest post number. Because otherwise, suppose suppose sorry suppose this component, which is C, received the highest post number, and it is not a source, meaning there is some other strongly connected component C prime that has an incoming edge to C, then that would mean that this has a higher C prime has a higher post number, and that is contradicting to property 2, what we just discussed, right? Is it clear what I'm saying? Okay. So to summarize, we can get a vertex. We can get a vertex. The highest post number, if you check, that will be a vertex in a source strongly connected component. And before that, we said that if we start explore from a vertex in a single strongly connected component, then we'll recover the entire strongly connected component. But now, so we have two things. One is that we have a result, or we have an idea saying that how to recover a single strongly connected component by starting exploration from a vertex there. Plus, we have a way to identify a vertex in a source strongly connected component, which is do DFS and you find the vertex with the highest post number. Okay. The question is now, we need a vertex in a sink, but we have a way of identifying a vertex in a source. Is there a way to use the identification of the source, vertex in a source, to get a vertex in a sink? So you need X, but you have a way to get Y.
By changing the direction in the graph,
By changing the direction of the
direction of edges in the graph.
precisely, yeah. So what we can do is simply consider a graph where all the directions are flipped to the opposite, right? Suppose this is our graph G, right? Which are the sources here? This is a DAG, I think. Yeah, this is a DAG. Which are the sources in this picture? In this blue picture? S is the
is
only source
P,
here.
Q, T.
Q is not a source. Q has incoming edge. Right? The only source is S. Source is a vertex or a component that has no incoming edge. So here the only source is S. And there are two sinks, R and U. There are two sinks. Sink is something that has no outgoing edge. Okay. So P has incoming and outgoing, Q has incoming and outgoing, T has incoming and outgoing. So they are neither. And if you flip the directions of these edges here, like the graph here is the reverse graph. It's the same graph, but all the arrows have the opposite direction. You see that R is a source, U is a source, and S is the only sink. So to get a graph with the so if you take GR, where you reverse all the edges, all the sources become sinks and all the sinks become sources. So what we can do is to run depth first search. Like our problem was that we need a vertex in a sink, but we have a way of getting a vertex in a source. So what we'll do is we run depth first search in the reverse graph. So G superscript R, I'm in the reverse graph, right? This is a reverse graph. Right? We run DFS on the reverse graph and then find a source there or a vertex in a source there. And that will be a vertex in a sink in the original graph. Right? Is it clear? So now the question is, how do we construct such a graph? This I'm not going to elaborate, but in linear time, you can just go through the adjacency list and make a new adjacency list at the same time as you're going through. It's not that difficult. Okay, I think you can try it as an exercise. So you can think about it. Now, what do we do? Like we have a way of identifying a vertex in a source strongly connected component, and we are reversing the graph first to obtain a vertex in the string strongly connected component. And then what do we do? We just use the same idea again. So the entire algorithm is this. This is the entire algorithm to recover the strongly connected components. So what you do is you first take the reverse graph. So construct the reverse graph, right? and you run depth first search on the reverse graph. Okay, so while doing this, you could do it in any order, like any type, any vertices. You pick any vertices. Then, like, when you have multiple vertices to choose, you pick any one, right? So, but the vertex with the highest post number here will be in a source of the GR, which means it will be in a sink of the G. Now what we do is, now we run depth first search in G now, but now we have an ordering of the vertices. Okay, so whenever you have multiple choices, let's say, like whenever we in our like examples, whenever we had multiple choices, we just did alphabetical. But now what we'll do is, whenever you have multiple choices, we will use the ordering that we recover here. What is the ordering? The ordering is the ordering of the vertices in step one. So whatever post numbers you obtain in step one, you order the vertices as per the decreasing order of the post numbers, right? So that ordering is what we will follow. So when a vertex is there and you have multiple paths to explore, you pick the path that comes first in the ordering. If there's only one path to explore, then there is not much to decide. Okay. And by this, what we are assured to do is that the first vertex, for instance, that we'll pick in this ordering will be necessarily in a sink of the of sink strongly connected component. So we'll entirely complete that will entirely before when you complete exit the exploration from that vertex, you would have recovered exactly that strongly connected component. And then you, like we did for connected components, then you increment a counter before you start a new exploration, and there again you use the same ordering. So there in the remaining graph, you will pick a sink in the remaining graph. So it may not be like it may not have been a sink in the original graph, but it will be a sink in the remaining graph. Meaning here there is only one sink. So maybe, but once you remove this component, then you have two sinks. Like suppose this GHIJKL is removed, then CF is a sink once that is removed, and D is also a sink. So whatever is the next vertex in the ordering could be either from D or from CF, right? And then you repeat the same thing till you. So basically, every time you exit, you start exploration. You start exploration from a vertex. When you exit the vertex, you would have recovered the vertices that you have explored would exactly be the strongly connected component. And when you start the next exploration from a vertex that has the highest, that comes as per this ordering in step two, and the exploration will give us another strongly connected component, and so on. So basically, we are doing depth first search twice. The first time on the reverse graph, and the second time on the original graph itself, but by the ordering that is dictated by step one. Right? The post numbers in step one give us an ordering, and that's what we do in step two. Yes, and there. So basically, it's twice DFS, and with some bookkeeping where you keep a count of how many times you called explore from the top level. So this is also O of B plus C. So basically 2 times DFS. So this is also O of V plus E time. Right, so that completes. So I've shown you depth first search, then how to recover connected components, how to recover what depth first search means in directed graphs, topological sort, and strongly connected components in directed graphs. Right. So, and all of this can be done in linear time, meaning O of V plus E time. And assuming the graph is given in adjacency list format. And that completes the part on depth first search. Any questions on this? Okay, so this I wrote this yesterday. I will share it again with you, but these parts were already there in the shared notes yesterday. So most of the discussion on DFS, almost all of the discussion on DFS is from this book, Algorithms by Dasgupta, Papadimitriou, and Vazirani. I think uh, some draft is available for free in their homepage itself. I think when they first, it's a draft version. I don't know if the yeah, it's probably close to the book, but it's called a draft, so you can get it the PDF for free. Yeah. And the discussion about asymptotic notation, etc., was from CLRS. And even the discussion that we will have after this on breadth first search and Dijkstra is going to be from CLRS, or mainly from CLRS, but slightly modified. Okay. Are there any questions?
Sir, what will be the time complexity for this step 2?
Step 2, okay, that's a good question. Very good question. So now, how do we order the vertices in the decreasing order of post numbers? So what one can do is you can have a separate array. We will not get, so this will not actually require extra time. Can be done in parallel to step 1. So what we can do is when we you could fill up an array in the reverse direction. Whenever we exit, when we complete the exploration at a certain vertex in step 1, right? In step 1, then we could fill up we could create the ordering here as per that. So the first vertex that you exit will have the lowest post number, and that vertex you store in the rightmost end of the array, and then you start filling up that array from right to left. So you don't really end up spending extra time. Is it clear what I'm saying?
Yes, okay.
Yeah, so we don't really end up spending any extra time here. Yeah, I didn't really explain how that is done, because if you have to actually sort them, that will require v log v time or something, which can be more than b plus c, right? If the number of edges is linear, then b plus c will be lesser than v log v, but we don't need v log v. We don't need to sort. Any other questions? Okay, I think then in that case, we'll conclude the discussion on DFS now. And I discovered I had slides for the next topic that I'm going to talk about. Okay. So I had at some point I had prepared, so I'm using those slides. Okay. So the next topic is breadth first search. Okay. So the goal of the objective is something similar. It's a traversal algorithm on graphs. It's again another fundamental graph algorithm, but um, there is a significant difference in the way that we do breadth first search versus depth first search. So in depth first search, what we do is you start exploring from a vertex, and then whenever you find a way, you keep going that way, right? So you keep a lot of loose ends. So in DFS, what you do is like you start here, then you find a way, you go here, you go here. So there could be other ways here. So right, so you keep going, and so on. And then when there are no ways left, you come back, and then that's what you do. In 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 breadth first search, what you do is completely different kind of approach. You start from a vertex, let's say call it S, then you go through all its neighbors, right? Then you go to all their neighbors, right? All their neighbors that have not been discovered. Then you go to the next level, right? So there could also be edges like this. Um, there could also be edges like this, but those are already discovered. So we do a like you completely look at all the possibilities and then you go to one step and then come back, one step, come back. And once you're done doing everything one step, then you take the second step from all of this, and then you take the once you do all the two-step things, then you do the third step, and so on. So do you see the difference? It's a your exploration happens significantly in a different way, right? Right. So this is algorithm pseudocode. So there are a couple of things I want to just quickly talk about. There is initially all the vertices are white, um, and then you except for the source vertex. The source vertex is the vertex from which you uh, source vertex is the vertex from which you start the exploration S. And so you have also a function D, right? So D is assigned to infinity for everything, and only for S, D is assigned to be 0. So the D will eventually going to be is eventually going to be the length of the shortest path. Okay. Okay. Just one second. This right. It is better. Then you also have this thing pi, which will come to later. Pi is the parent, which will come to later. Then you have so initially all the vertices are white. When you get, and then you have something called a queue. Okay, a queue is a data structure that does the following. It resembles a real life queue where like you have, let's say, people standing, let's say A, B, C, D, and so on. Let's say this is the direction of the queue. So then A will be first exiting the queue. So think of this as is like a like a like a ticket counter, or in some place where you buy tickets, or like in a bank, like a service counter. So A will be first served here, and then he will exit the queue. And in the meantime, if some G comes, G will stand at the tail of the queue. So a queue is nothing but a data structure where people are served first in, first out. So that's the main thing. It's a data structure where people are served first in, first out. So this is something that is needed for the breadth first search. We need a queue data structure. I will not explain how to maintain this because what we are doing is not really data structures class. I'll just talk about the algorithm, and there are different ways to implement queues. So we'll not get into that. So okay. And then so basically what we do is we initially have a queue with some vertices, and then we'll see whenever a vertex is at the front of the queue, that will be dequeued, and then its neighbors will be enqueued, and this will keep happening. Okay. So maybe I'll illustrate with an example. Okay. So this is the graph that I have. It's an undirected graph. So we'll just do it on undirected graphs, I think, for now. And this will be our starting vertex. S will be our starting vertex. Okay. So initially, this D value is assigned to be 0 for S and infinity for everything else. Is it clear? Okay. D value is assigned to be 0 for S and infinity for everything else. And notice another thing that you can keep noticing during the execution is that all the vertices were initially white. Then S came into the queue. So now S is gray. Everything else is still white. Okay. So the queue is written at the top here. Okay. Next step is so now S is the only vertex in the queue. So now you will dequeue this S. Okay, so you DQ this S, which means you look at its neighbors and you will NQ them. So the neighbors of S are G and R, right? So R and G are NQ'd. Okay, so there is no order, arbitrary order in the slides. We have R NQ'd before G, and both of them, the D value is assigned to be 1. And why is it assigned to be 1? Because S had value 0, so you have one more than that. Okay, so now S is out of the Q, DQ'd vertex, so S has color black. R and G are inside the Q, so they are colored gray, and their D values are 1 more than that of S. Okay. Next step, you will DQ R. Right? And when you DQ R, now R becomes black. You NQ F because it's neighbor, and you D value of F is 2 because D value of R was 1. Okay. And now F is in the queue, G is in the queue. G was already in the queue, G remains to be in the queue. So now the next vertex that is DQ'd is which is the next vertex that is to be DQ'd?
G.
G is the next vertex, right? So when G is DQ'd, what will be the vertices that will get into the queue?
B, A, D. Sorry, B and A.
B and A. And what would be the D values for B and A?
3.
3? No.
Uh,
It will be
2.
2 because you look at which is the vertex that is resulting your inclusion. So G is causing B and A to be discovered. So G had the value 1. So B and A will have the value 2. Okay, so now G is DQ'd, right? G is DQ'd. So now the queue has A and B has been queued. F was already in the queue, so F will continue to be there in the queue. Okay. Now, what is the next vertex to be DQ'd?
F.
F.
F. And so now F will become black. And which are the vertices that will be NQ'd?
Nothing.
No, what?
Nothing. So F will be DQ'd. There is no neighbors that are already discovered, that are not already discovered. So F is just DQ'd, so the queue just shrinks. Right. So now the next one that will be DQ'd is A, right? Because that is at the head of the queue. And which are the vertices that will be discovered?
D.
D and
E.
E. And what are the D values?
Will it be 3?
3. Yeah, both of them will have D value 3, right? So A will be DQ'd, so A is black. Now E and D are NQ'd, so both of them have gray color, and both will have D values 3, right? So now, so A is DQ'd, right? A is DQ'd, and E and D are NQ'd. So now the queue has length 3 vertices in the queue. Now the next vertex to be DQ'd is B, which has only a single neighbor C. So B will be DQ'd and C will be NQ'd. B becomes black because it's DQ'd. C will become gray because it is NQ'd. And C has gray color and has D value 3. The next vertex to be DQ'd is what's the next vertex to be DQ'd?
E.
E. And which are the NQ'd vertices?
H and I and J.
And all of them will have D value 4 because all of them are discovered from E. So all of these 3 of them will have D value 4. And now E is DQ'd and J, H, I are NQ'd. All of them have D value 4. So now we have 5 vertices in the queue. C, D, I, J, H. Sorry, not in that order. D, C, J, H, I, right? And next, next thing that you can notice, next thing that will be DQ'd is D. So there's nothing to be NQ'd because there's no vertex neighbor that is undiscovered. There's no neighbor that is undiscovered. So we'll just DQ D, D will become black. That's it. Next you will DQ C, C will become black. Next you will DQ J, and again J's neighbors are I and H and E. All of them have been discovered, so there is nothing. We'll just DQ J. J becomes black. H becomes black and DQ'd. I becomes black and DQ'd. So now the queue is empty, right? And that's it. That's the end of the algorithm, or that's the end of the process. Right. So right now I'm not talking about a separate exploration from each unvisited. I don't want to do that. Unlike what we did in depth first search. So we are not, even though these are vertices in the graph K and L, we are not going to be exploring them right now. Okay. So there's a reason that there's a thing that I want to discuss, because of which I don't want to start exploration on this. Okay. So this is the end of the algorithm. Okay. Is the algorithm clear? What we do?
Sir, is S randomly chosen?
No. S could be chosen because one property of breadth first search that we'll soon see is that this actually gives the length of the shortest path from the source vertex. So depending on, perhaps we need to find start exploration from a certain vertex. Maybe we need to find the shortest path from a certain vertex. So maybe that will dictate from where you start the exploration. So S could be anything. So if you start S, the exploration from any vertex, you will get different values, but these are the D values will be the shortest path lengths. So maybe there is some vertex from which you need these values. So you should start your exploration from there.
Okay.
Yeah.
Okay.
Any other questions? Is the algorithm clear? Is what the description clear?
Yes, sir.
Yeah, thanks. This is the thing again. So initially color everything white. Maybe now it makes sense to go through it again. Initially, every du is infinity for everybody. And pi u I will come to later. Pi I will come to later. Then S becomes 0. S is colored gray, and then you NQS. Okay, so initially the Q is empty, and then you NQS. So one thing that you'll notice is that everything is white. When you NQ, you make it gray, and when you DQ, you make it black. So it's like white. When you touch the Q, it becomes gray, and then when you exit the Q, it becomes black. And then you keep DQing. So DQ will automatically return the element that is in the front of the Q. So this will return the element or the vertex at the front of the queue. So the next customer to be served, or the next vertex to be served, and here next customer to be served will be automatically DQ'd. So this first in first out process will be respected. Okay, so first in first out. And then you look at all the neighbors of U. So this indicates the neighborhood of U. Okay, maybe I should say that. List of neighbors of U. Right? Then, so now for each neighbor of U, you check if it has color white. Meaning, color white is another way of saying has it been discovered before? Because once it is discovered, the color will no longer be white, right? If it is of color white, then you make it color gray and you NQ it, and you also update the D and pi values. So D value will be 1 plus the D value of U, and pi value will be just U. So I'll come to the pi value later. So D is just 1 more than the D of U, because you were discovered through U. D value will be 1 more than that of U. Right? And notice that we do this step only if the color is white. If color is gray, meaning already if you're in the queue, or if color is black, if you've already been in the queue, then you don't do this, right? And that is this part, the if part. And then for each we do this, and you NQ them. And after that, once all of this is completed, you color U with black. So meaning black has been dequeued, we do all this and then you exit the queue. So color U black. So black are those vertices that have been in the queue. And this, you keep doing this till the queue is empty, right? Because you keep enqueuing also. So you keep dequeuing till you run out of vertices in the queue. Clear? This is just the same algorithm. Earlier we went over the algorithm kind of pictorially or kind of descriptively. Now we are just seeing the pseudocode. What is the running time of this algorithm? How much time does it take? So yeah. Let's see step by step. How many times is the enqueue function called?
V times.
It is called V times because once a vertex is enqueued only once, because once it is, you only enqueue. So initially S is enqueued, and you enqueue only vertices that are white, meaning once you enqueue it, they are never white again. They are never recolored as white. So enqueue happens at most V times. So maybe I'll use another color. So at most V enqueues. So which means at most V dequeues also, right? Because you only dequeue those things that are enqueued. Right? Because in the earlier example, we saw some vertices are never enqueued. Right? How much time does how much time does this step take, this for each V in the neighborhood? How much time does that take? And inside this, it's a constant time operation. Once you have for a fixed V, all of this is like one step operation. But how many times will we do this step for each? Like how many times is this loop running? This is running as many times as V has neighbors, but overall, how many times will we do this?
Degree of that vertex.
Sorry?
Degree of that vertex.
Degree of that vertex for that vertex, but if you across all the vertices, how much does it take?
At most E times
At most?
the number of edges.
Yeah, it depends on a certain thing. So it is either E times if the graph is directed, or it is 2E times if the graph is undirected. Because if a graph is undirected, then V will be in the neighborhood of U as well as U will be in the neighborhood of V. So this part, right? This part happens. Sorry. Maybe I'll just say at most 2E times or less than or equal to 2E times. Right? This part happens at most 2E times. And each vertex, the color operation, each vertex is colored exactly once white, at most once gray, and at most once black. So like you don't color white. So there's a clear progression: white, gray, and black. So you don't go from white to gray, then gray to white, then gray to black. These kind of like, or black to white or something. So once it is recolored as gray, and then once more it's recolored as black. So everything happens. So the total running time is yeah. So this has each enqueue operation, dequeue operation takes constant time. Let's just assume that without getting into how enqueue dequeue is implemented. And totally queue operation takes O of V time. And each list in the adjacency list, meaning each neighborhood list, is scanned once. This requires theta E time. Again, this is assuming that the graph is provided in the adjacency list format. Okay. And And initialization takes O of V time, and even the recoloring, everything takes O of V time. So the total running time is O of V plus E, assuming the graph is given as adjacency list format. Okay. So this is the running time.
Yes. So, what do you mean that initialization required?
Initialization, by that I mean things like this. The queue is setting the queue to empty, and making the all color all the vertices white, and assigning everything d of u to be infinity, pi of u to nil, all of these things. Basically, you are assigning some values for all the vertices. That's what I mean by initialization. Like everything till this point. Okay. 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 Is it clear? Okay, so next, so this is the time complexity. So this is very similar to uh, 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 depth first search, right? Because there also we were looking at the only thing is that there we did not have any queue data structure, and whenever we were seeing a path, we were just following it, right? But still, we also had this thing about we also had this thing about looking at all the neighbors, and you are going depth first into in the neighboring list. But there, instead of the queue, we are actually doing recursion. Okay. Here there is no recursion, right? So there is no, you're not calling this process again from here. There, explore was called in a recursive manner. So implicitly, there is something called a stack data structure was being used to implement the recursion. But here we are using a queue kind, and there is no recursion. Okay. A stack is something like the opposite of queue, meaning it has this property of last in, first out. So think of like you have a like stack of plates and you keep stacking things on top, and you when you need a plate, you take the first plate on the top. So you whatever you put at the end will come out at the beginning. So this is the opposite of a queue. But anyway, these are kind of yeah. This is just if you don't get it, it's okay. Any other questions? Okay, so next, I think what I want to talk about. Okay, one other point is that the colors are just something that is easy for us to visualize, but equivalently, the colors don't really add significant information. Equivalently, we could just check instead of asking if the color is white, you could just check if dv is infinity, because because whenever the color is white, dv is infinity or d of v is infinity, and you when you make the color to be gray, you are assigning a non-infinite or rather finite value. So it is equivalent to check if dv is infinity. Okay. Okay. So now I want to talk about the other thing that I discussed earlier. That two things. One of them I don't have any proof or anything, but the cool thing about breadth first search as against depth first search is that these d values actually um, give the shortest path distance from S to that vertex, right? So maybe I'll just draw some things. And the pi values, let's see, the pi of S is assigned empty, right? Pi of S is empty. Yeah. Isn't pi of S? Okay, pi of everything is empty, and so pi of S is also empty. And then pi of each V is the U from which you discover it, right? So I'll just represent the pi using arrows. So the pi function is pi of one, this G is S, pi of R is S, pi of F is R, right? So So these arrows indicate the pi function. Basically, these are the pi functions. So two things I'm claiming, one of which we'll discuss in a bit more detail. One is that these values, the d values, are the shortest path distance from S to that vertex. So d of I is 4, and the shortest path length is 4, right? And d of j is 4, so shortest path length is 4. D of b is 2, so the shortest path length is 2. And not just that, you can actually recover the shortest path by, like, if you want to know the shortest path from S to B, you look at what is the pi value at B, it is G. And then what is the pi value at G, it is S. So you can recover the shortest path by following these pi values. So the pi value gives us, leads us back to S from wherever we are, assuming there is a path from S to that vertex. So for K, there is no pi value because K is not reachable from S. Right? So what I want to do now for the rest of today, I don't think we'll have time for Dijkstra's algorithm. But for the rest of today, I want to talk about why this is true. So we'll only talk about the d values being the distance. Okay, so by the correctness, I mean d value shows the distance. So some notation, we will use delta SV to denote the shortest length path, the length of the shortest path from S to V. By length of the shortest path, we don't have any weights on edges or anything. So it's just number of edges. Okay. Okay. And the main theorem is that once the BFS is run from the on the graph G, starting from the source vertex S, every vertex that is reachable is reached. Okay, every vertex that is reachable is indeed reached. And for all the vertices V, the d value will be equal to the shortest path length. Okay. So in fact, we'll basically just show 2, and 1 is kind of easy to see once you have to. Okay. Any questions? Okay, so this is we'll have a kind of a proof, but yeah. So there are some things that I will state, and I will prove everything. So if you don't follow the proof, please ask questions. Okay. So we'll prove it by contradiction. So what is the statement? We'll say that dv is equal to the shortest path length. So assume that is not true. Assume there is some vertex for which this is dv is not the shortest path length, and if there are, and you choose the vertex for the reason we're trying to get to a contradiction. That's how we will. So we assume there is some vertex for which this is not true, and then we will get to a contradiction. So let you pick the word. Suppose there are many vertices where this is not true. Pick the vertex with the smallest distance for which this is not true. So pick the vertex with the smallest actual distance. Again, delta SV is the distance from S to V, and dV is the algorithm value, okay, for which this is not true. The first claim is that dV is greater than or equal to delta SV, meaning dV is not smaller. Okay, this is the claim 1. We'll prove this, but right now we'll just use this and go ahead. But later I'll show you the proof. These are not each one of them is not that difficult to see. Like they're all, I just broken them down into very small things. Now choose a shortest path from S to V. So now S to V, there is a shortest path. There could be many shortest paths. So like if you look at over here, I don't know, in this graph, are there multiple shortest paths? Maybe not. In this graph, there are not multiple shortest paths, but in general, you could have multiple paths of the shortest length. Okay. Choose a shortest path from S to V. Now let U be the vertex that is that appears just before V. Okay. So there is S. somewhere you reach u, and then there is v. Okay, so in the shortest path, let u be the vertex that is preceding v, right? And we chose v to be the smallest, the vertex with the smallest distance, such that dv is not equal to the actual distance. So the actual distance for u is smaller than the actual distance for v, because the shortest path for u is also this, right? So for that means for u, we must have delta su is equal to the du value, right? Because if delta su is not equal to du value for u, then we would have chosen u instead here, u here instead of v. So delta sv is basically delta su plus 1, because whatever is the shortest path from s to u plus 1 edge. But then delta su is equal to du, because we assume that v is one with the shortest path length where it is violated, right? So we had this claim that dv is greater than or equal to delta sv, which we will prove, and we assume that dv is not equal to delta sv, which means together they imply that dv is actually strictly greater than delta sv, right? So that's what I've written below. So dv is greater than delta sv, which is du plus 1, which same thing over here. Same thing, I've written the same thing over here. Now, so now we just reach a contradiction. Now, when you dq u, so again, remember u is the predecessor of v in the path. When you dq u, where was v? That's what we are trying to figure out. When u is dq'd, either v is not in the queue, or it is already in the queue, or it has already gone into the queue and got out of the queue. We'll show in each case that this cannot happen. Each of these three cases, we'll show that this cannot happen. That's pretty much going to be the proof. In each of the case, we will show that dv cannot be strictly greater than du plus 1. Suppose when u is dq'd, v was not in the queue, meaning v was white colored, which means that when so because v is a neighbor of u, you will discover v, and dv will be set to du plus 1. But here we are saying dv is strictly greater than du plus 1. So that's a contradiction, right? Suppose v is black, meaning v has already come into the queue and gone. That means v has already come into the queue and gone. And then we will say that in that case dv will be less than or equal to du. If v was dq'd before u, then v will be less than or equal to du. This is another claim that we will see. Okay, meaning everything in the queue, the queue values only get bigger, never get smaller. Okay, so again, this is a contradiction to this. Here we are saying that dv is strictly greater than du plus 1, and this contradicts that. And the third thing is that v was gray, meaning when u is dq'd, v was already in the queue, meaning v got into the queue through some w that was before, that was dq'd before u, right? Meaning v was here, u was here, and w was here, and we got into the queue through w, and which w was already dq'd before u, right? So, and because v got into the queue through w, dv is equal to dw plus 1, right? But by claim 2, we said that claim 2 is saying that if v was dq'd before u, then dv is less than or equal to du. So since w was dq'd before u, dw is less than or equal to du. Hence, this quantity is less than or equal to du plus 1. And again, that is contradicting this thing, that dv is strictly greater than du plus 1. So in each of these three cases, there is a contradiction. Right. So this completes the proof that for every vertex V, if it is reachable from S, dV is going to be the number of steps in the shortest path from S to that vertex. So the other things show one is this: every vertex that is reachable from S gets discovered. For all the, so one is that everything that is reachable from S does get discovered, because otherwise this you will not get this value. Otherwise it will remain infinity. So step one is not really that difficult, or it's kind of straightforward. So I'm not getting into that. So what remains to be shown are claim 2 and claim 1. Claim 1 is that we assume that dV is strictly greater than or equal to, greater than or equal to delta SV, right? It never becomes smaller. And the claim 2 is that the things in the Q, whenever a vertex is dq'd, let's say V is dq'd before U, then dV is less than or equal to du. Any questions so far? Okay, so maybe we'll go ahead with the proofs of the two claims. So before that, there's one other short claim that we will just show. Again, these are all very simple things. It's not that you can try proving it for yourself if in case you don't follow our discussion right now. Suppose UV is an edge, then delta SV is at most delta SU plus 1. Meaning if UV is an edge, then the shortest, what we are saying is the shortest path length from S to V, S is somewhere here, the shortest path length from S to V is at most 1 more than the shortest path length from S to U. Why is this true? Why is this true? This is not that difficult to see. It's very simple actually. So consider the shortest path from S to U, right? Consider one of the shortest paths from S to U. There could be more than one shortest path. Now you append this UV edge to that shortest path. So you get one path from S to V. So that is one way to reach V from S. And that has length delta SU plus 1. So one way to reach V is take the shortest path from S to U and take this edge. But of course, that is just one way to reach V from S. So the shortest path from S to V could be could be smaller than this, but it cannot be bigger than this. So one way from S to V is to go through U. So that gives you a distance delta SU plus 1. But this is just one way. It could be that there are other ways. So that gives you this inequality. This is clear, right? At least this one is clear. Any questions so far? Now we have two more things to show. One is that for any vertex, dV is lower bounded by the shortest path length. And
Excuse me.
yeah, thank you. The other thing is about the Q. Like whenever a vertex is dq'd first, it will have a lower d value. That's the second thing that we need to show. This is also like in the slide, it may seem like the proof is long, but it's really just common sense things. This is using induction. So when we are beginning, all the vertices have d value infinity, except S, which has d value 0. But for S, the shortest path is also like there's no edge. So if you start at S, you have a 0 length path. So ds is equal to 0. Right? And for all the other vertices, dv is set to infinity. So certainly infinity is something bigger than the actual shortest path length. So the base case is true. Now, when does it get updated? We update it as part of the algorithm when some vertex is dequeued, meaning, and some vertex is discovered. So let's say U is dequeued at some point of the algorithm, and V gets discovered as a neighbor of U, right? So U is dequeued and V gets discovered. So by assumption, du is greater than or equal to delta SU. And when du is dequeued, the algorithm assigns dv to be 1 plus du. This is what is assigned by the algorithm. And du is at least delta SU by the induction hypothesis, this one. And delta SU plus 1 is greater than delta SV, which we just said before. We said it as claim 3, right? We said it here. Delta SV is at most delta SU plus 1. So dV is at least delta SV, or dV is not smaller than delta SV. So that even when a vertex is getting discovered, this is true. So it's basically just induction without much difficulty. This is claim 1. Claim 2 is if you look at two vertices V and U, if V is dequeued before V is dequeued before U, then the D value of V is smaller than the D value of U. It's simpler to show, or it's easier to show something that is stronger statement. So at some point, let's say the Q contains these values, V1 to VR. R vertices are there in the Q, where V1 is at the front, meaning this is the next, V1 is the next vertex to be dequeued. In that case, throughout we will have D of V1 less than D of V2, this kind of relationship. Plus, we will also have so all of them are less than or equal to the previous one. Plus, we have the thing that D of VR is not more than D of V1 plus 1. Okay. So it could be that if D of V1 is 2, then D of VR cannot be 4, for instance, 4 or 5 or something. It is at most 3. It can be 2, but it cannot be more than 3. It can be 3 also, but it cannot be 4. So all the values here will be 2, 2, 2, 2, 3, or 3, 3, 3, 3, 4, 4, 4, or something like that. It's in non-decreasing order, plus the last value is at most 1 more than the first value. And this kind of is stronger than this statement, right? So I just show claim 4. Again, it's induction. So when you NQ S initially, this is trivially true. Whenever you DQ, suppose you have all these vertices. When you DQ V1, clearly for the rest of the vertices in the queue, it holds. And dVr is at most dV1 plus 1. But then dV1 plus 1 is at most dV2 plus 1, because dV1 is less than or equal to dV2. So it's DQing is actually easier to see because the queue is only getting smaller. And when we have NQ, suppose we are NQing something. Let's say we are NQing a vertex V. So we NQ'd V because a vertex U was just DQ'd. Okay, U was ahead of the Q. And U was ahead of V1 in the Q. Right. So when U was in the Q, by induction hypothesis, this and the statement must be true. Right. And we assign dV to be du plus 1. Right. So we already have dV to be du plus 1. And we already had dVr was at most du plus 1. So dvr is less than or equal to dv, because dvr was already at most du plus 1 because du was ahead of the q. So dvr is less than or equal to dv. That is one requirement. And yeah, and the other thing was that we needed so other thing is, I think, not that difficult to see. We want this, right? We want dv to be at most dv1 plus 1. Why is this true? This is true because dv is equal to du plus 1 and du is less than or equal to dv1 plus 1. Yeah, so this is why this is true. So both the properties are satisfied. And that completes the proof of correctness of breadth first search. Rather, the proof that breadth first search actually gives you the length of the shortest length paths, or the paths of the shortest number of edges from the source vertex to all the other vertices that are reachable from it. And the running time is O of B plus E, assuming it is given in adjacency list format. Any questions? Okay, so we started at 4. Maybe I'll just talk for 5 more minutes, but I will not really. Okay, this is just one more point. One more point is that the loop, we have an invariant. Invariant is some statements that are always true during the execution of an algorithm. One other invariant is that the Q will always consist of the gray vertices. It's not that, like, when we described the algorithm, it should have been clear, but I'm just saying this. Okay, so I will not go into great detail right now about the next algorithm, because it's like 5:20 and you've had, like, maybe this is the 4th session of the day. So I don't want to go into detail, but I will just talk briefly about shortest paths. Shortest paths when we have weights on the edges. Okay, so breadth first search gives us the shortest length paths, where by length you mean the number of edges in the path, right? So now the question is, what if I actually give weights on edges, something like this? Okay, so now I have a source vertex here. Now I want to find the shortest length path from. So what is the shortest length path from S to B? What is shortest length path from S to B? There are many ways to reach S to B, right?
AB.
Sorry, AB. So that is the path of loop 11. Anything else? So what about this DB? That is 14.
That is also possible.
No, but that is 14, right?
Okay.
There is this path DCB that is of length 13. But is there anything else?
SDAB.
SDAB, right? Because the single edge path from S to A is not the shortest to reach A. So you can SDAB, it's like 5 plus 3 plus 1, it is of length 9, right? So yeah, so the thing is SDAB is of length 9. So now how do we, so given this kind of situation, what is the shortest way to reach a vertex from a single source? So the problem that we look at here is it's called single source shortest paths. Right? Meaning we have a single source from which you want to compute the shortest paths to all the vertices in the graph. Got it? Right? So can we use breadth first search here? If you use breadth first search, will it work?
No, since it
Not work.
uses arbitrary neighbors.
I'm sorry.
Since it uses arbitrary neighbors.
Right, we already saw an example, right? So like breadth first search would probably return the shortest path to be SAB because it contains only 2 edges, but the one that uses 3 edges is actually short or has less weight, 5 plus 3 plus 1, right? So this is actually better. So we cannot use breadth first search. And our discussion tomorrow will be, so we'll talk about this tomorrow. We will only look at the case when we'll only look at the case where the weights are integers and non-negative integers. Okay, so we will not look at the case when there are like negative values. So integers is just to like make it keep things simple. It's not really a significantly significant condition, but we'll keep it non-negative because we don't want the complications of negative. Negative things will bring some other complications. Right. So I'll not get into, yeah, maybe I'll talk about it tomorrow. So typically there are 2 types of shortest path algorithms. One is this type, single source shortest path. The other is called all pair shortest paths. Compute shortest paths for all vertex pairs u comma v. So given u and v, we want all possible u and v, we want the shortest paths. So this is given a source S and V, compute shortest paths from S to all V in V. So what we'll see only this. Okay, so we'll see only this. So we will see only single source shortest paths. Yeah, there are algorithms for all pair shortest path also, and that too for a specific or for some under some specific conditions. We'll see this algorithm called Dijkstra's algorithm, which gives us a single source shortest path when you have non-negative weights on edges, right? So like this is an example. This is the Dijkstra's algorithm. We'll talk about it tomorrow. But before that, suppose in this graph, suppose you want to find the shortest path using breadth first search. Is there some way you can do it using breadth first search? Suppose you can modify the graph somehow. Given this graph, you can construct some other graph. And can you get the shortest path in this graph by using BFS in the other graph? Is the question clear? Is the question clear?
Yes. Maybe rank the neighbors according to the
Not
weights.
really. No, ranking the neighbors may not really help.
Please repeat the question.
My question is there a way to like construct another graph, modify this graph, and construct another graph so that the shortest, like let's say this is graph G. Is it possible to construct a graph G prime such that if we apply breadth first search on G prime, you get the shortest path in G? Like, is there a way to replace the edges with something? So here is an edge of length 10. And in breadth first search, we are just counting the number of edges. So how would you modify this edge, for instance? Or let's say modify this edge, for instance. Basically, you want to make this transition to count twice. So what we can do, one reduction is to basically split the edges. So this edge can be split into two. So by making a new vertex here. So now I will have two edges. You understand what I'm saying? So in my new graph, instead of one edge from D to C, I'll have an edge from D to some intermediate new vertex, and from that vertex to C. So to reach C from D, I will have to like basically make two edges. And similarly, this edge will be like I'll have one vertex here, another vertex here, and another. So this edge will be split into three edges. And likewise here, it will be split into 10 small edges. Right? So that's what I was saying as G prime. Like we can do this, right? Each edge you split it into, if the weight is 5, you split into 5 pieces. If the weight is 3, you split into 3 pieces. If the weight is 1, you just keep it as it is. Right? And that will give us, and if you do breadth first search on that, then you will get the shortest length path on that will be equal to the shortest path here.
Is there anything else that can be done with D? Like when we increase the value of D, we add the weights of the this thing edges, and then
We'll do something like that only. So that will be our algorithm that we will discuss tomorrow. Right. We'll be actually, instead of there we just updated D with 1. So now we will actually be updating it with the weights. So that will be the algorithm that we'll see tomorrow. It's the Dijkstra's algorithm. But that will involve, so that I want to talk later. But this is one easy thing that I could say by using a connection to the breadth first search. Yeah, I think I'll let you think about this, and maybe tomorrow we'll talk about Dijkstra's algorithm. It's 5:30 already, and in the I think list of topics that I had said in the beginning, I said two more things. One is minimum spanning tree, and then I think max flow min cut. The time may be tight to do like Dijkstra's algorithm, minimum spanning tree, max flow min cut. Maybe I will do only some topics, or maybe I'll do the algorithms without proofs. Maybe I'll think over it and let you know tomorrow. Okay. Yeah. I think that's all from me for today. And yeah, thanks for staying with me till 5:30. Yeah, that's all. Thank you.